Question. So for question 1, we have to obtain the Fourier series expansion of the waveform below. So to solve this type of question, first we have to know what is the period of this graph. So if you look at the graph here, the period is equals to 2 pi. Once you've already obtained the period, then you can substitute it into the omega naught, which is frequency formula. So 2 pi over t equals to 1. And once you've already gotten the period and frequency, then you need to solve for A0, AN, and BN. So A0 is the DC component, whereas AN being the even and BN being odd. AN and BN are the AC components. So when you want to solve for these three components, you need to refer to this table 17.1. So it will most likely in your exams, they won't be giving the formula. So please memorize the formula. And this is how you solve for A0, AN, and BN. So over here, these are the formulas for A0 being 1 over T ZT dt, and AN being 2 over T ZT cos n omega naught T dt, and Bn being 2 over T ZT sin n omega naught T dt. So for this question, you just need to do some basic integrations, and A0 you get negative 1 over 2, or in decimal form, you get negative 0.5. So A0 and AN is simple. And but if you look at AN, you take a look at sine n pi. If you remember the table 17.1, which I shared previously, sine n pi is actually equals to 0. So that is why the answer for AN is equals to 0. Okay. And for BN, BN is the same as AN. You just need to refer to the table and do some basic conversions. And because this graph is an odd graph and not an even graph, so when you want to solve for n, just assume n is equals an odd number. In this case, we assume n is equals to 1, and you get the answer 6 over n pi. And for those who actually tried to put in n is equals to 2, which is an even number, they might question why they have a value. But in this answer, we are showing 0. Well, that's because the graph is actually an odd graph. So we'll just assume that the n equals to even equals to 0. Once you've already obtained A0, AN, and BN, then you can substitute it into this formula, which we have ZT is equals to negative 0.5 plus 6 over n pi sine nt. Next, for question 2, we have to give the Fourier coefficients A0, AN, and BN of the waveform, and we also have to plot the amplitude and phase spectra. So it is the same as the previous question, only in this case, we have to do some plottings, which is the amplitude and phase spectra. So, as usual, we have to find out what is the period, which I'm sure most of you know by now how to find the period, which period is equals to 4. And once you substitute the period into omega naught, we get pi over 2. Next, we can solve for A0, AN, and BN. Okay, so just like in the previous question, only this time because the graph here is a bit I would say weird. because it's not a sine wave and it's not a square wave, but it is a weird graph that looks a bit like a stair. So whenever you see an odd looking graph like that, so you have to actually write down the expressions of the graph. So we have here GT is equals to uh, amplitude 5 at 0 up to 1 and amplitude 10 at 1 to 2 and 0 amplitude at 2 to 4. So once you've already obtained the expressions, then you can put it inside A0, AN, and BN. So which A0 is equals to 1 over T, T being 4, 1 over 4, 5 dt, 10 dt, and 0 dt. And do some integrations and you get the answer as 3.75. Next, to solve for AN, AN is pretty much the same as the previous question, just do some integration and you get the answer. And for BN, yes, you just do some integration and do some simplification and you get the answer 5 over n pi cos n pi over 2 plus 1 minus 2 cos n pi. Now, some of you might be looking at the answer sheet and then notice that there is a difference in the answer with the answer sheet. The answer sheet, it said something like 5 over n pi cos n pi over 2 plus 3 minus 2 cos n pi. Whereas for our answer, we get as 1 instead of 3. So I have actually checked with this answer with all of you during last week's tutorial. And it seems that all of us got the answer as cos n pi over 2 plus 1 instead of plus 3. So this will be the answer for BN. And one more thing, you might be wondering, why is it in the first question we had to substitute n as an odd number and n as an even number? So why is it we are not assuming n is equals to 1 when the graph itself is an odd graph? Well, that's because in this question, we actually have to plot the amplitude and phase spectra. So we will be assuming n into a graph form. So we don't have to be assuming what value of n this is. So we can proceed on plotting phase and spectra. Okay, so based on the answer you got for A0, AN, and BN, so this is before you start plotting the amplitude and phase spectra, first you have to construct this table. So let's say we just put n equals to 1 up to 8. And the AN, and then you just substitute n values for AN and BN, and you get the answer for AN. When n equals to 1, AN is equals to negative 1.59, for example. But please remember, when you want to calculate this in the calculator, for AN, BN, and amplitude being the capital AN, make sure for these three formulas here, make sure you set your calculator into radians instead of degrees. Whereas for phase, you set it into degrees. So you just use your calculator and you get the answer. But for phase, you actually have to refer to the trigonometric functions, which is the if you look at the drawing I did on the right side, we have first quadrant, second quadrant, third quadrant, and fourth quadrant. So if we look at n equals to 1 at the face tab here, so initially the face we got 71.57, but we also have to refer to the quadrant rules. So if you remember, an is an even, and even being cos, and bn odd being sine. So we have here an being cos, cos is negative, and bn being sine, sine is positive, which is positive 4.77. Okay, so we have negative cos and positive sine. So if we look at the quadrant, it is inside the second quadrant. So because it is inside the second quadrant, we have to do 180 degrees minus with 71.57. And we get the answer as 108.43. And so yes, when you want to solve for phase, make sure you also refer to the quadrants as well. Okay, so if you want more examples of this, you can refer to your textbook, page 762 minus 766. And this is after you have plot in the amplitude graph. And as you can see here, it is much easier to plot compared to body plot. And this is the phase plot. Next, we're going to be solving for question 4. Question 4, in the circuit shown in figure 4, the Fourier series expansion of VST is this formula, find V naught T. So, if we look at VST, 3 is the DC component, and 4 pi over n sine n pi t is the AC component. So for this type of question, first we have to find the solve for the DC component and also the AC component. So for the DC component, there is a rule that the capacitor and inductor value will be 0. So because that is the rule, so we can just use a simple voltage divider to find V naught of this DC component. So we have V naught is equals to 0 after we have put in omega n equals to 0, and Vs is equals to 3. Vs being for the DC component. Now, for the AC component, because we don't assume inductor and capacitor to be 0, so we unfortunately have to use nodal analysis to solve this. So for nodal analysis, you just have to remember what goes in and what goes out. Make sure you initialize what is the node you choose to solve for nodal analysis, and you just once you solve it and you get V naught is equals to Vs over 1 plus j 2.5 n pi minus 5 over n pi. Now from this voltage output you get, then you can solve for the amplitude and phase formula. So overall, the AN phase, which by the way, when we look at the top equation here, AN, some of you might think that it's AN less than phase. Actually, it's basically a phase symbol. It's not less than, it's phase. Okay, so we get AN phase equals to 4 over n pi plus j 2.5 n square pi squared minus 5. And from this equation we get, we will know what is the amplitude. Amplitude equals to 4 over square root n square pi squared minus, by the way, if you look at the answer sheet, you might notice that for the amplitude, it is different from the equation that I've written here. Because in the answer sheet, it is 4 over square root n square pi squared plus instead of minus. So the reason why I did minus instead of plus is because they were squaring the n square pi squared and also squaring j squared. So j squared is equals to -1. So because j squared is equals to -1, so it will be minus. So that's why I put in n square pi squared minus 2.5 n square pi squared minus 5 squared. Okay. And then for the phase, which we can find from the equation AN phase as well. So this 2.5 n square pi squared minus 5 over n pi is basically after we have put in the denominator n pi at 2.5 n pi. Yeah. Then once you've already solved for amplitude and phase, then you can put it inside the formula. V naught t is equals to an sine n pi t plus phase volt. Next, for Fourier series. Oh wait. Okay, so for question 5, determine V naught t in figure 2 if VIT is equals to 5 signum t equals to -5 plus t ut volt. So for this question, this 1 signum is equals to 2 over j omega. So because input voltage, we have here 5 signum. So 5 signum will be 5 times 2 over j omega, which we get 10 over j omega. So, and from the circuit that we have in the question, we can find h omega is equals to 4 over 4 plus j omega. And once we obtain h omega, then we can substitute it into the transfer function v naught omega is equals to h omega times vi omega, which we get 40 over j omega times 4 plus j omega. And because the denominator is a complex denominator, then we need to solve this into using a partial fraction. So once you solve using partial fraction, then you get 10 over j omega minus 10 over 4 plus j omega. And from this, you can refer to your Laplace transform table, and you get -5 plus 10 times 1 minus e -40 ut volt. Okay, so now for question 5, we have to determine the Fourier transform of Vt in the circuit shown in figure 10. So to solve this question, we just solve this using nodal analysis. And remember, in equals to out. So you have to determine which current goes inside V0 and what goes out of V0. So once you've done that, then you just rearrange the formula and you get V omega is equals to 2j omega times 4.5 plus j2 omega over 2 plus j omega times 4 minus 2 omega squared plus j omega. Okay, so now we're going to tutorial 4. So to solve for tutorial 4, you can refer to this table which I have made here to solve for z parameter, y parameter, and h parameter. Make sure you memorize these rules, okay? So for the first question involves the y parameters. Question 1, in the circuit shown, find the y parameters of the two-port network. If you remember the table previously, to solve for y11 and y21, we have to apply the voltage source V1 and also short circuit V2, which I have drawn the circuit over here so that you can visualize it better. And to solve for y11, you just use the Ohm's law, I equals to V over R, and you can solve for y11, which you get 1 over Siemens. Next, for y21, y21 also simple. You just apply some voltage divider rule and you get to solve for y21, which is negative 1 over 12 Siemens. Then to solve for y22 and y12, you have to apply the voltage source V2 and short circuit V1. So to solve for y12, you use voltage divider rule, which I did an acronym here, VDR. So you just solve, and you get y12 is equals to negative 1 over 12 Siemens. And it's the same for y22. You just use basic Ohm's law, and you get y22 is equals to 1 over 2 S. Then, once you've already obtained the values for y11 up to y22, then you can put it inside a matrix form, which y is equals to 1 over 8 Siemens, negative 1 over 12 Siemens, and negative 1 over 12 Siemens, and 1 over 2 Siemens. So for the y parameters, remember the units is in Siemens because it's y, admittance. Now for the next question, question 2, we have to solve for the h parameters for the two-port network shown below. So first we have to solve for h11 and h21, where we have to apply the voltage source V1 and short circuit V2. So if you want to visualize it better, you can just draw the circuit. You just draw the voltage source at V1 and just short circuit V2. And just like question 1, you just solve for H11 and you solve for H21. Then we can solve for H22 and H12. So we have to first apply the open circuit V1 and put in voltage source at V2. So then you solve for H22 and H12. And remember that in question 1, I say that for y parameters, the what do you call? The units will be in Siemens. But for the h parameters, it's kind of like a mixed bag over here. Because for H11 we are using ohms, and H12 we are using 0.4 ohms. But for H21 we are not using any units because it depends on the formula. if the formula results in Siemens, then it will end as Siemens. And if the formula doesn't result in any units, then it would just be negative 0.4. It is the same for H22, which we get 0.27 Siemens. Then we move on to question 4, which this time it deals with Z parameters. So for Z parameters, we have a matrix form. Z is equals to 10, negative 6, negative 4, 12. And from the circuit that we have here, we have to find I1, I2, V1, and V2. So to solve this type of questions, we have to construct a lot of equations using substitution method. Before we move on to solving using the substitution method, let's solve using the matrix form of Z matrix first. So if you remember the how to solve for matrix, we have V1 is equals to 10I1 minus 6I2. That is the first equation. And V2 is equals to negative 4I1 plus 12I2. So if you don't remember how to solve for matrix, then please refer on the internet on how to solve for this matrix. And from the circuit, we can solve using the mesh analysis, which we get V2 is equals to negative 10I2. And that is the third equation. So, then if we were to look at the circuit again, we can also solve it using mesh analysis, which I believe we can actually change the current source to become the voltage source using the source transformation, and we get it as 12 volt. So you just solve using mesh analysis, negative 12 plus 6I1 plus V1, and we get V1 is equals to 12 minus 6I1, and that is the fourth equation. So now that you've already got 4 equations, then you can substitute it and you get the values. I2 is equals to 0.1463 amps, and you got the remaining values for I1, V2, and V1. Now for the last question, which is question 5. Compute the Z parameters of the circuit shown below. And as we can see here, we have a dependent voltage source for I1. To solve for Z11 and Z21, make sure you apply a voltage source at V1 and you open circuit at V2. So you just solve just like Q1, the previous 2 questions. But at V2 is equals to 20I1 plus 4I1. That is because we are dealing with a dependent voltage source. So it will be equals to 24I1. Once you've already obtained V2, then you can substitute it into Z21 equals to 24I1 over I1 equals to 24 ohms. Now to solve for Z12 and Z22, we have to open circuit the voltage source and apply a voltage source at V2. So you just solve for Z12 equals to 20 ohms. And for Z22, since I1 is equals to 0, because it is an open circuit at V1, So I1 will be equals to 0. Hence, 4I1 will be equals to 0 as well. So you just solve for Z22, which we get 30 ohms. And we can compute it into the Z matrix, which is 25 ohms, 20 ohms, 24 ohms, and 30 ohms. That is all.